In lesson 13B, we're going to be looking at formulas. It said in an earlier lesson, you determined that when you're traveling 45 miles per hour, you will travel 264 feet in 4 seconds, or 66 feet per second. What if you apply the brakes? Predict the braking distance, the distance a car will travel after the brakes have been applied. Honestly, at this point, it's hard to know how much that's going to change things, how quickly pressing the brakes makes a difference. I'm going to guess that if we applied the brakes, instead of going 264 feet, maybe we would go 150 feet, but I really don't know. All right, in this lesson, we want to understand that a variable is a symbol that's used to represent a quantity that can change. Some variables in a formula can be held fixed in order to analyze the effect that the change in one variable has on another. In other words, in real life, the results of things like braking distance depend on a lot of things. How fast is the car going? How good are your tires? How much friction do you have between your tires and the road? What are road conditions that day? How good are your brakes? So there's a lot of factors that might make a difference why somebody would be able to stop quicker than another. All right, so here is our formula for braking distance. And you can see it's a pretty complicated looking formula. It tells us that the braking distance is equal to V0 squared. Well, V0 is the initial velocity. How fast was the car going when you hit the brakes? D is the braking distance, of course. G is something they're calling the roadway grade. We're going to write it, it is a percent, but we will write it as a decimal. So it tells us something about road conditions. The lowercase f is the coefficient of friction between the tires and the roadway. The coefficient of friction is typically going to be some number between 0 and 1. There are situations where there's extremely high friction in other applications, but for a road, definitely between 0 and 1. It says good tires, you might get 0.8 to 0.85. The larger that number F is, and the larger that capital G is, the shorter that stopping distance is going to be. Lowercase g is the acceleration due to gravity. It's 32.2 feet per second squared, or 9.8 meters per second squared. I feel like we're in a physics class because this is very much a physics type of formula. Since g is a constant, this formula has 4 variables. So let's think about that. So here's our formula. Why is my pen not working this morning? Uh-oh. Hold on. See if now my pen wants to go. Let's back up one more. So here's our formula. Distance equals V0 squared 2g f plus g. Now, this little g is really a constant because it does not change. It is not a variable. So our variables, if we just want to think about what are our variables, my goodness. Our variables are this initial speed, f, and g. Okay, These are what we might consider the independent variables, and then D, the stopping distance, is the fourth variable. The stopping distance depends on these other three. Now, if we know F and G, if we're on a certain road with certain conditions, then we can see that our stopping distance just depends on the square of the velocity. It says consider a condition in which the coefficient of friction is 0.8 and the roadway grade is 0.05. Write a simplified form of the formula using these values. So here's our formula. I assume we're going to be working in feet, so I'm going to put in little g, as 32.2 feet per second squared. F, of course, is going to be 0.8. The roadway grade is 0.05. So now we could actually say that our distance just depends on the initial velocity squared. I can work out the rest of this. That's 2, that's 32.2, that's 0.85, or use a calculator and multiply. What is 2 times, and that's supposed to be a 2 right there, 32.2 times 0.85. It's just the number 54, 54.74. Calculate the braking distance when the speed is 45 miles per hour or 66 feet per second. So we're going to use that formula we just had. So our speed is 66 feet per second squared. Feet per second, and then we square all of this. This has units of 54.74 feet per second squared. The units when we get our answer will be feet. So 66 squared divided by 54.74. And we're getting 79.6 or about 80 feet. So if you're driving 66 feet per second when you hit the brakes under these particular different conditions, it will take you about 80 feet to stop. When the speed is 45 miles per hour, calculate the braking distance for the roadway grades of 0.15 and 0.30. So we're going to keep that that F is going to still be 0.8, but we're going to change the value of G. So let's do that. We know the stopping distance, 2G F plus G. So if we are going 66 feet per second, that's going to be squared. G, if we're working in feet, it's 32.2. It's feet per second squared. F was 0.8, and we're going to do it for 0.15. This is going to actually make the stopping distance shorter because we're going to have a better roadway grade. So let's go ahead and kind of do this step by step. 66 squared is 4356. Where's my 43? 356. This is going to be 64.4, but I have to add the 0.8 plus 0.15. That's 0.95. Or 61.18. So for a road grade of 0.15, we're getting 71 feet. So we're going to stop just a little faster. If we change this number from 0.15 to 30, and I'm not going to show you all the steps this time because you can do this yourself, 66 squared. This comes out to 61 feet. So road conditions definitely make a difference. All right, so move on to another formula. We're going to talk about the formula for body mass index. The body mass index, or BMI, is a measure of body fat based on height and weight. It is a standard tool for helping judge the amount of body fat you have. Carrying excess body fat puts people at greater risk for health problems, such as heart disease, cancer, diabetes, and stroke. BMI can be calculated using a simple ratio based on a person's height and weight. If your BMI is considered to be in the normal range, which means it's between 18.5, your BMI is considered normal if it's between 18.5 and 25. BMI is considered a better predictor of health than weight alone. Jot down your ideas about why this statement would be true, then share with another student. Well, we're not in a classroom, so we're going to kind of omit this. But BMI basically says, for a person your height, is your weight an appropriate weight? In this, we're going to look at substituting for one variable, which can give us a simplified formula. It says BMI can be calculated with the following formula, where the weight is in pounds and the height is in inches. Joe is 5 feet 10 inches tall. Substitute his height into the formula. So let's look at that formula one more time. I need to write it down. Our formula is weight over height squared times 703. So your BMI equals your weight, which needs to be in pounds, divided by the height squared, and height needs to be in inches, times 703. Well, 5 feet is 60 inches. So Joe is 60 inches plus 10 inches is 70 inches. I got that simply by going 5 times 12 equals 60. So his weight, they didn't give us his weight. So we know it's going to be his weight over 70 squared times 703. So all we've done so far is put in his height. You have created a new formula that applies only to people who are Joe's height. What are the only variables that remain in your new formula? So our new formula is that our BMI equals your weight over 70 squared times 703. Or we could even simplify that again. We could say it's your weight over 4,900 times 703, because 70 squared is 4,900. So now the only variable is BMI and weight. Your BMI depends on his weight. Using your simplified formula, calculate Joe's BMI if he weighs 175. How does it change if he gains 10 pounds or if he loses 10 pounds? So BMI, if he's 175 over 4,900 times 703, now we just use our calculator. 175 divided by 4,900 times 703. We see that his BMI is 25.1. I believe, let's go back and look at the safe range. 18.5 to 25. So he's just right at the upper edge of considered to be a safe or a good weight for his height. Just barely past it. Now, if he gains 10 pounds, we know he's going to be over it even more. So 185 divided by 4,900 times 703. And his BMI is now up to 26.5. This would be considered overweight. It would not be considered obese. It's not extremely unhealthy, but obviously they consider this to be about 10 or 15 pounds too heavy. If he lost that 10 pounds, and he only weighed 165, whoops. That gets his BMI down to about 23.7. So that's nicely in, that's a very healthy weight. Honestly, this would still be considered healthy. It's just right on the edge. And when it comes to things like this, even BMIs are not exact. A doctor's going to look at other factors in determining if your weight is appropriate. All right, this should probably just ask you to think about what steps you had to take. We needed to plug in for our variables. It's important when you solve this, when you have a formula like this, it's important that you square the height first. That is part of our order of operations. I'm sure you probably all have learned something called please. Some people called it PEMDAS. But that please, excuse, my dear Aunt Sally. Better capitalize Sally. We always do things in parentheses first. That's the P. We always do exponents. So simplify inside parentheses. When you're looking in those parentheses, first you do exponents. Then these are one step. Multiply and divide. Whoops. Oh my goodness. Multiply and divide from left to right. Now, some people just want to do everything from left to right, but you've got to do those parentheses and the exponents first. You do not add and subtract it. You go through and you multiply and divide as you see fit. And then the last thing you do, and these are that go together also, is then you're going to add and subtract from left to right. So, parentheses first, simplify any exponents, then working across the problem, multiply and divide, basically as you come to it. In this case, when it's written like this, you would do the exponent, height squared, weight divided by height, times the 703. It would not change your answer if you said, oh, I think it means I need to do, first you're going to have to square the height, but you could do weight times 703, then divide it by the height squared. You would get the same answer. All right, in this section we're going to look at target weights. So if you've seen a video running backwards, what happens? For example, if the original video shows a person opening the door, getting into the car, and starting the car, what does the reverse video look like? Well, that's going to show them starting the car before. It's going to look like, instead of getting into the car, that they're getting out of the car, right? Then you're going to see them closing the door. It's going to look like they closed the door they just opened when you see it in reverse. All right, we're going to talk about the fact that multiplication and division are inverse operations. Basically, that means division can reverse or undo multiplication. Multiplication can reverse or undo division. All right, here's our BMI formula. It says, recall that a person is considered to be underweight if his or her BMI is less than 18.5. He's considered to be overweight if his BMI is between 25 and 30, and obese if a person's BMI is over 30. Philip is 6 feet 3 inches tall. What is Philip's BMI formula? Determine how much he would weigh for each of the following BMI values. Record your steps for part A in words. Well, let's just work through part A. We know that BMI is weight divided by height squared. We know the weight has to be in pounds, the height has to be in inches, times 703. So 6 feet 3 inches tall. Well, 6 feet, to change that to inches, I have to multiply it by 12, is 72 inches. Since he is 6 feet 3 inches, we see he is 75 inches tall. His BMI formula is his weight divided by 75 squared times 703. If I want to go ahead and square 75, that's 5625. So to get his BMI, it's his weight over 5625 times 703. All right. We basically have two variables, this one and this one. What if I want a formula that says weight equals? I want to get a formula for weight. I have to undo what's being done over here. So if I want to get rid of this times 703, I need to divide by 703 on both sides. I'm going to do that in red so you can see what I mean. I'm going to divide by 703. I'm going to divide by 703. Notice that's going to make this go away. So now I have a formula that looks like this. The BMI over 703 equals the weight over 5625. Okay, I'm trying to get weight all by itself. So the way I get weight all by itself now is I said, well, look, I'm dividing by 5625. Let's multiply by 56 times 5625 times, I got kind of out of room here, 5625. This will cancel with this. And so now I have a formula that looks like this. Your weight is equal to your BMI over 703 times 5625. Now that's only a formula for Philip or anybody else who's 6 feet 3 inches tall. But we went backwards to reverse it. So let's find, if we know his BMI, let's find his weight for each of these numbers. So I'm going to put 18.5. So for part A, it will be 18.5. Well, let's write this down. 18.5 over 703 times 5625. And that says that he weighs 148 pounds. He's quite slim at 18.5. That's the very minimal for a healthy weight. If his BMI is 25, which is so it's still a healthy weight, but it's the other extreme. That's a 7 right there. Hope you can tell that that's a 7. 25 divided by 703 times 5625. And this one, he weighs 200 pounds. So at 6 feet 3 inches tall, there's quite a range of healthy weights. All right. How much is obese? Anything over 200, and Philip is getting too heavy to really be considered to have a healthy weight. If he gets up to a BMI of 30, at this point, he's 240 pounds. All right. So Sally's weight is 115 pounds. What is her simplified BMI formula? How does it differ from Philip's? Well, in this case, we don't know height, we know weight. So we know BMI equals weight over height squared times 703. So for Sally, since we know the weight, her new formula looks like this. So the two things we don't know are BMI and her height. With Philip, the two things we didn't know were weight and BMI. We knew Philip's height. It says Sally has hit a growth spurt. 4 months ago, she was 5 foot 3 inches tall. Now she is 5 feet 6 inches tall, but she has maintained her weight at 115 pounds. Find her BMI both 4 months ago and now. How has it changed? So her BMI is 115 over her height squared. Well, 5 feet is 60 inches plus another 3 inches. So originally her height was 63. So height squared times 703. I'm going to do 115. I have to divide it by that 63 squared. Her BMI was 20. So actually 20.4, so perfectly healthy in between that 18 and 25. Actually, I think it's 18.5. That's our minimum. So 115. If she's 66 inches, that's our 60 inches plus 6 inches. So she's 66 inches tall. That gives her a BMI of 18.6. So she's much slimmer, but she's still considered to be a healthy weight. It says Sally continues to grow taller while maintaining her weight. She eventually reaches an unhealthy BMI of 18. How does this problem differ from question 1 where you were given BMI values for Philip? I'm not sure what they mean, but we have a final BMI here of 18. We can certainly see how tall she is as opposed to what her weight is. Let's see what it says to do. Let's go back. Let's find out how tall she reaches. Her BMI was her 115 over her height squared times 703. Let's solve this. Notice the thing we don't know here is her height. See if we can figure out how we can get her height. This is 18. This is 115 over height squared times 703. The first thing that I would probably do here is go ahead and divide by 703. This gives us a new formula that looks like this. 18 over 703 equals 115 over her height squared. When I have a problem that looks like two equal ratios, the easiest way to solve it is to cross multiply. Let's multiply 18 times height squared. So I get 18 height squared equals 703 times 115. It's going to be a big number. 703 times 115. I get 80,845. I am trying to get the height alone. So I'll change color so you can see the change. Let's divide by 18 because we're trying to solve for height. I will get height squared equals 80,845 divided by 18, 449. 4,491.4. I want her height, so take a square root. Let's do that. Let's change our color again so we can see the new step. We're going to take a square root. This will just give me her height. So her height is 67 inches. That is the same as saying 60 inches plus 7 inches. Why did I do 60 inches? Because I know 60 inches is 5 feet. So she's 5 feet 7 inches tall is her height when she has that BMI of 18. All right, that's the end of this video.